The Earth acts like a giant magnet, with the north pole of the magnet at the geographic south pole and the south pole of the magnet at the geographic north pole. That's why a compass will rotate such that the north pole of the compass points towards the geographic north pole. If you follow the magnetic flux lines of the Earth's magnetic field as they emanate from the geographic south pole and wrap around and enter the geographic north pole, you'll notice that if you're at the equator, the Earth's magnetic field is parallel to the Earth's surface, and if you're at one of the poles, the Earth's magnetic field is perpendicular to the Earth's surface. And if you're somewhere between the equator and a pole, the Earth's magnetic field makes some angle with the Earth's surface. What we are going to do is measure the magnitude and the direction of the Earth's magnetic field where I am located, which is West Lafayette, Indiana. The needle of the compass is aligned with the horizontal component of the Earth's magnetic field, and on this dial we see that it's pointing at 330 degrees. Now I'm going to take the compass and rotate it 90 degrees. The compass needle is now aligned with the Earth's magnetic field. We see that the needle has rotated from pointing at 330 degrees to about 37 degrees. So the angle the Earth's magnetic field is making with the horizontal is 67 degrees. I have a power supply connected to a 15-turn coil, and in the center of the coil I have a compass. I don't have a current flowing through the coil yet, so the only magnetic field is the field due to the Earth, and so the compass needle is pointing towards the north. Now, as I apply a current to the coil, a magnetic field will be generated, and at the center of the coil, it will be pointing in the eastward direction. So now I'm going to apply a current to the coil. So as I increase the current to the coil, you can see that the compass needle is starting to rotate towards the east. So now I'll increase the current to the point where the needle is pointing exactly northeast. So at this point, the field generated by the coil, which is in the eastward direction, is equal in magnitude to the horizontal component of the Earth's magnetic field, which would be pointing towards the north. The current flowing through the 15-loop coil is 0.156 amps. Here's an illustration of the magnetic flux density field produced by a current loop. Notice that at the very center of the current loop, the magnetic flux density field is perpendicular to the cross section of the current loop. We are going to apply the Biot-Savart law to a current loop to find the value of this magnetic flux density field at the center of our loop. And then by multiplying by the number of turns of the coil we're using, we'll get the value of the magnetic flux density field at the center of our coil. Here is a current loop of radius rho, and we're going to use the Biot-Savart law to determine the magnetic flux density field at the center of the loop, the origin here. So a differential length along the current loop has a distance rho d phi, and it's in the phi direction. And so we make the substitution for dl, rho d phi in the phi direction. This unit vector here, A sub uppercase R, is a unit vector pointing from the current element to the point we're trying to find the magnetic flux density field. So it will be minus A sub rho. The radius, or distance from the current element to where we want to find the magnetic flux density field, is rho. So now the cross product between these two unit vectors is a unit vector in the z direction, so that's perpendicular to the plane of the current loop. We factor out some of the constants. This integral here of d phi from 0 to 2 pi will add up the contributions to the magnetic flux density field of all the current elements around the loop. And that integral will just be 2 pi. So for the magnitude of the field, we have mu sub 0 I over 2 rho, and the direction is in the z direction. Okay, so the magnetic flux density field in the center of the loop is mu sub 0 I over 2 rho. That's for one loop, and if we have n loops, we just multiply by the number of loops. Let's measure the diameter of the coil. And it's about 14.3 centimeters. We can now determine the measured horizontal component of the Earth's magnetic field. Our coil had 15 turns. The permeability of free space is 12.6 times 10 to the minus 7 henries per meter. The current we measured was 0.156 amps, and the diameter of our coil was 0.143 meters. Okay, so that works out to be 20.62 microtesla. We also measured the angle that the Earth's magnetic field makes with the horizontal, and that angle was 67 degrees. So the magnitude of the Earth's magnetic field will be our measured horizontal component divided by the cosine of our measured angle of 67 degrees. And that works out to be 52.8 microtesla. So let's see how well we did. Okay, so here I have a plot of the angle the Earth's magnetic field makes with the horizontal. So let's zoom in, and we're in West Lafayette, Indiana, right about here. So this line is 60 degrees, this line is 80 degrees. So in West Lafayette, Indiana here, it's indicating about 68 degrees, which is pretty close to our measured value of 67 degrees. Our measured value of the magnetic flux density field of the Earth's magnetic field was 53 microtesla. So here I have a map of the Earth's magnetic flux density field as a function of position on the Earth. This line here is 50 microtesla. This one is 55 microtesla. So here in West Lafayette, the value is 53 microtesla, which is essentially what we measured.